We'll begin with Mark Hancock from McGill, and he'll talk about clustering for content distribution.
So good morning, ladies and gentlemen. First, before I begin, I'd like to thank the organizers. I did my PhD at Cambridge about 10 years ago, so this has been a wonderful opportunity to come back. I haven't been back since I finished, and visit all my old haunts, and in between a lot of punting and visiting the orchard for some afternoon tea and many visits to various pubs. I've also managed to attend a few talks, and it's been an interesting set of talks during this week, and I think the next couple of days will be very interesting too. Today I'm going to be talking about clustering for content distribution. It's some joint work with a couple of my students, Hani Masood and Salim Tabatabaye, and also my colleague Mike Rabat. So the application focus is mobile social networks. I'm not going to defend this application focus to the death. I'm not 100% convinced about the practicality of them or the economic feasibility. So if you have questions along that line, maybe we'll just discuss them afterwards. But I think they're very interesting, and they do have some potential. So the basic idea is that if you have a bunch of people wandering around, users of a wireless network, when they come together and they meet each other, there's the potential for a local wireless communication. You can have either a low power 802.11 point-to-point communication, which exists under maybe the 802.11 system that's working as a general channel, or you consider Bluetooth. So both of these mechanisms provide you with some bandwidth that's really not being fully utilized in current wireless networks. And another point may be that these two types of communication are cheap as compared to, say, the 3G cell phone type system, where people are really paying for the bandwidth that they might utilize. So there are settings where both the ISP may want to reduce the amount of what I'll call primary bandwidth that's being consumed by the users in times of peak demand. So a good example is sort of the firmware updates for the iPhone, where you see that it can really take a long time for certain people to download the update. I was talking 4 or 5 hours in some cases, because the system becomes congested. And so what we're proposing with these mobile social networks is perhaps with these types of settings where you'd like to distribute content throughout the entire network, you can consider using this point-to-point bandwidth as an alternative mechanism to distribute the content. So some example applications: software firmware updates, database information, push-based video on-demand systems. And the basic gist is you exchange data using local connections whenever you meet and come into the same range. So our focus, just to make it a little bit, we're not talking about point-to-point routing through this sort of mechanism, which is a slightly different problem. We're really looking at network-wide dissemination of content, and we're assuming that the contact process is stationary and ergodic and independent of the server interactions. So the way in which people interact with one another is not being dictated by the data that you're downloading. And we're going to be addressing two problems. One is minimizing the age of content, assuming in the case that we have frequent updates. This might be the scenario where you're getting updates of news or some sort of information like this, where you'd like it to be fresh, and your utility is going to be a function of how fresh that news is. And the second problem we're going to look at is minimizing the consumption of primary bandwidth. So how can you set up the situation so that you're making the most of these point-to-point communications and limiting the primary bandwidth consumption? So the age of content problem was looked at by Yanadis and a group of people at Thompson. The setting there is that you have a fixed server bandwidth, so the server might be the 3G system that's downloading content to individual users, And your goal is to select the download rates to individual users in order to maximize the aggregated utility, a social welfare type problem. And the user utilities would be non-decreasing functions of content age. So they show that this is a convex optimization problem once you have certain pieces of information. The second problem is minimizing this primary bandwidth consumption. So what we might consider there is that you have something like a fountain code representation of a file. So a fountain code is a rateless coding system where you take a file that requires k packets and start coding this and distribute packets to individual users. And once you've acquired any set of those packets that you've created, you can reconstruct the original file. So the problem setting there is to select the number of packets to download initially to each user. And after a specified time interval, you're going to have to complete the file for each user. So what that would mean is that if Rob happens to be a very social individual, I might give him a lot of packets. He's going to meet a lot of people and disseminate his packets to them. At the end of the day, Daryl up the back might still be missing packets, and I'm going to directly, as a server, inject the packets that he needs to complete this file. So you have a combination of how much bandwidth are you going to use initially, and then how much bandwidth are you going to have to use at the end to make sure everyone's got this file within a certain period of time. So the difficulties, well, I mentioned that this is a convex optimization problem. The trouble is that the calculation of the gradient, you really need to calculate the gradient for each user j with respect to the injection rate or how many packets you download at user I. So you have these pairwise gradients that you need to compute. These gradients are a function of the distribution of the time taken for information to travel from user I to user j. So again, if I inject content to Rob, how long does it take to get to Daryl? And this can be a little bit problematic once I start talking about large systems. So thousands of users, I'm talking about millions of pairwise gradients that I need to compute. It becomes a very cumbersome estimation task. And even if I'm going to do this in a distributed fashion, then I've got problems on my hands. The second thing is that in order to do these estimates of distributions of the gradients via the distributions, I'm going to have to take quite a number of samples. And if the contact time between Rob and Daryl is a long one, it's going to be very hard for me to get enough samples to have accurate estimates of those contact times. And what's going to happen then is I'm going to have high variance estimates and potentially poor solutions of who should I download content to and at what rates. So our approach is to cluster users. And then you can take two tacks. One is to approximate the estimation problem. So you can adopt a model where you say user I experiences the same percolation time or information diffusion time to any user j in cluster j. So sitting up the back, I see that Daryl is sitting next to Matt. Now I'm going to say, if I inject content to Rob, it's going to take exactly the same time to get to Daryl and Matt in terms of the distribution. So the estimation problem can be reduced significantly in size. The next thing I can perhaps do is approximate the optimization problem. So I can divide it into a two-level optimization problem, allocate the rates to the clusters first, and then decide within each cluster what are going to be the rates to the individual users within that cluster. And there, I don't need to know the global pairwise gradients, I just need to know the local pairwise gradients within each cluster. And I can go back and forth between these two layers of the optimization and get a reasonable approximation of the global optimization problem. So with this introduction, this is where the talk takes a different tack and becomes a graph clustering talk. So I'm not really going to talk much more about mobile social networks much at all. I'm going to start talking about graph clustering and what we might like to do in order to come up with sensible clusters and groups of people in order to make these good approximations both for the estimation and the optimization. So the graph clustering problem, given a possibly weighted graph, G, which consists of a set of vertices and edges and weights on those edges, which would represent similarities. And similarities in the context of mobile social networks are perhaps the contact rates between individual users. What I'd like to do is find a good partition of the vertices. So I take this set of vertices and break it into a group of clusters so that traditional clustering ideas maximize the similarity within clusters, maximize the dissimilarity between different clusters. And what that's going to lead me to is a simplified network representation. And this is where the two-layer optimization would come in. First, I might do the optimization on this very simple network on the right, and then that would allow me to do an optimization on a slightly more complicated network in the middle, looking just at individual clusters. Clustering in a graph involves three separate issues. First, how do I go about choosing the criterion? So what makes for a good clustering? If I'm going to do a certain partition, how do I say this partitioning is better than that partitioning? The second problem that I have is how do I choose how many clusters I should have in this partitioning? Like I have many choices. I could have 15 clusters, or in this case 5. What is better, 15 or 5? And then finally, given this criterion and this choice of the number of clusters, I need to come up with an algorithm in order to find, hopefully, the clustering which maximizes this criterion and identifies the best partitioning. So looking at these three issues that we need to face and thinking about the context of information dissemination in mobile social networks, the three things that we'd like to achieve in terms of the criterion, we'd like to maximize the information dispersion. So if I inject, what I'd like to have is, I'd like to identify a cluster so that if I inject to any user in that cluster, it gets to every other user in the cluster fast. And this, if I have that property, then my approximation is going to be good to some degree, because if Matt is in the same cluster as Daryl, and I manage to get to Matt, then it's going to take a very short amount of time for him to infect Daryl. They're right next to each other whispering, so it's and that's going to make my approximation of the time it takes to get from Rob back to Matt and the time it takes to get from Rob back to Daryl, saying that they're equal effectively, a reasonably good one. So we'd like to maximize the information dispersion within each cluster. This can be related to graph conductance, but I'd somehow like to maximize the conductance within each cluster, and it will lead to the normalized cut criterion that we're going to focus on. Choosing the number of clusters, well, the only thing I'd really like to insist on there is that we have an automatic procedure for doing so. I don't really want to have to go in after the fact and choose the number of clusters based on inspecting a set of candidates. And finally, the algorithm, in order to do this, I really want something that's fast and scalable. So ideally, I want to apply this to tens of thousands of users in the network. In order for that to be applicable and for me to be able to do the clustering and the calculations in a reasonable amount of time, my scaling with the number of users in the network is going to have to be reasonably good. So some of the options as far as criteria that I could choose to optimize in this clustering problem. Modularity, there's been a lot of work on this topic, and maybe we'll have a talk, the very following talk, we'll perhaps address some of the issues of modularity, seeing Mark Newman's effectively the pioneer on this approach. There are information theoretic approaches. Roswell and Bergstrom provide the algorithm InfoMap. You may be familiar with that also because it forms the basis of eigenfactor, which is used to assess citation counts. And then finally, what we're going to focus on is minimum cut or minimum normalized cut. And this has a relationship to spectral partitioning and some of the references there of people who've contributed to the work. So to make the problem a little bit more concrete, I'm going to define these two things. The weight between two clusters V1 and V2, or more also called the cut, is just going to be the sum over the nodes in V1 and the nodes in V2 of the weights between each of those sets of nodes. And then the degree of a cluster V1 is going to be the sum over all the vertices in that set, in that cluster, of the individual degrees of the nodes. Those individual degrees are just the outgoing weights to all other nodes. So J belongs in the entire set of nodes at the start, the weights from each individual node. And so when we talk about minimizing a cut, what we're interested in is minimizing this W, V1, V2. And so minimizing a minimum cut partitioning, we want to partition a graph into k subgraphs, and a standard formulation is to minimize the maximum cut between any two subgraphs. And there's an efficient solution. You can recursively find the minimum cuts that bipartition the graph. The problem with this direct minimum cut approach is that it really favors cutting small sets of isolated nodes. So you end up with some very small clusters because the cut increases with the number of edges between two subgraphs. So it's good to take away Matt and Daryl, who are an isolated little community, and put them in a separate room because they don't talk with anyone else. And what we'd like to achieve is a little bit more balance in the size of our clusters. So she and Malik proposed a bipartitioning scheme again to minimize the normalized cut. So the normalized cut of V1 and V2, a bipartitioning of V. We take the same thing, so it's the cut between V1 and V2, but now we're going to normalize those two terms by the degree of V1 and the degree of V2. And because these terms are going to increase as the size of the cluster grows, then you have some normalization in effect, and you have a preference for balanced partitionings. So the interesting, how has this been approached? Well, it's an NP-complete problem to find this best K clustering or best K-way n-cut problem. But if you can approximate the optimization of this criterion by putting it in the framework of a generalized eigenvalue system and solving for that relaxed system, it turns out that you can approximate it using the second smallest eigenvector of the normalized graph Laplacian. How does that work? Well, if I define D as an n by n matrix with D as its diagonal, and W as a matrix with all the weights between individual nodes, and then I have these little things K and B. K is just the degree of V1 divided by the total degree of V, and then B is K over 1 minus K. Those are sort of details that you don't really need to worry about. Then, with quite a bit of messy algebra, I can write down the minimization of the normalized cut for this bipartitioning in this framework. And if I solve this problem under the constraints that yi either has to be 1 or minus b, and I have this orthogonality condition, then the solution to this problem will be exactly the same as the minimization of the normalized cut. So that's still a hard problem. I haven't really done anything to help myself. But if I relax it and let yi take on real values, then I'm in the framework of a generalized eigenvalue system. I can calculate the second smallest eigenvector, and that's going to be the solution to this minimized normalized cut, minimum normalized cut. Effectively, what I have to do after the fact is decide whether yi is closer to 1 or closer to minus b, and I have to make the allocations accordingly. So k-way normalized cut, I've talked about sort of bipartitioning into two clusters. K-way normalized cut then is framed as the sum over the k clusters that you have of these, the weight from that individual cluster to all the other nodes in the entire network, normalized by the degree of that cluster. And it's equivalent to maximizing the normalized association, so minimizing normalized cut, the same as minimizing the normalized association, which is just what fraction of your weight joins nodes within you to other nodes within you as a cluster. You're now a cluster. And again, this problem can be solved by approximating using the k smallest, should be a little k, the k smallest eigenvectors, again, of the normalized graph Laplacian, and that allows me to map into Rk, and then I might cluster using something like k-means. So I've done a mapping from the graph using this eigenvector system into the space of reals, and then I can do standard clustering type algorithms. So what's the problem with these techniques, these spectral techniques? Well, they're slow. And so generalized eigendecomposition, you're talking about order n cubed algorithms. If I only want a smaller set of eigenvectors, then I can use algorithms that are much faster. But if I need k of them in order to do this clustering, eventually it's going to get down to what is the ratio between the kth and the k plus 1th eigenvector. And if that's small, the iterative algorithm is going to need a lot of iterations. The complexity still grows quite large with n. And I mentioned at the start, we'd like a fast algorithm. So if you run any of these spectral algorithms on even reasonably sized graphs, the execution time starts going up and up. And there's also some issues with the stability of those algorithms. So Dillon et al. Proposed an algorithm that avoids eigendecomposition, and what they effectively showed is that weighted kernel k-means is equivalent to k-way normalized cut minimization, and then proposed a multi-level algorithm that's similar to Metis for people who are familiar with other clustering algorithms. Involves greedily coarsening the graph, clustering that coarsened graph, and then refine and expand. It's a nice algorithm, but it's a non-convex optimization, and it's subject to local minima when you try and solve it. So the proposal here that we're making as a group is a greedy agglomerative normalized cut. So a very simple algorithm that we're proposing is to greedily maximize the normalized association of this partitioning, starting from the bottom and going up. And for each edge in the network, you're going to compute the improvement in the normalized association by selecting that edge. You're going to select the best edge, and then you'll merge the vertices at each end of that edge into a new cluster. And then you compute the new equivalent graph that you've constructed when you've migrated from k to k minus 1 clusters. In terms of algorithmic detail, so looking at what we need in order to achieve this, this greedy agglomerative algorithm, what do we need to store and what do we need to update? What is our complexity going to be? Well, we need to store the degrees of each cluster, the weights, and this improvement matrix. And the improvement matrix is just equal to this fairly simple expression of, for two clusters, U and V, what is the weight between those two clusters divided by the sum of their degrees. And at each iteration, we're going to choose the pair that maximizes this improvement matrix. Once we've chosen the pair that maximizes this improvement matrix, then we're going to have to update the improvement matrix and the weights, and calculate the weights for that new cluster to all of its neighbors. And finally, the last step is just to calculate the new self-weight of the cluster with itself. So the computational complexity of this algorithm, Well, if there are m edges in this graph, the initialization of this matrix, you'd hope that it can be relatively sparse, is going to take order m time. And then if I use a data structure such as a heap, locating the maximal entry in that matrix, removing entries from that matrix, adding entries from that matrix, I can do all of that in order log m time. So those two steps are really not a bottleneck in terms of calculations. What's going to hurt me a little bit is updating the entries. And in the worst case, updating the entries at each level, I potentially have n neighbors for each cluster, n being in the worst case at the finest scale. I have the total number of nodes in the graph. You think maybe of a complete graph. And then at each one of these levels, as I go up and merge nodes together, I still have n nodes. So my worst case complexity is going to be order n squared, log m coming from the fact that each update search for a maximum is taking me log m time. More common, well, it really depends on how do these number of neighbors for each node grow with respect to the total number of nodes in the graph. And if that can be bounded by some factor that's related to the log of the number of nodes, then you get complexity that's a little bit closer to order n log m log n. Model order selection. So the second part of this problem was choosing how many clusters I should have in this partitioning. And what we think is that partitions at multiple scales may be of interest. I insisted at the beginning that we're going to choose one, but for now we'll assume that multiple of them are of interest. What we're going to look at is the relative improvement in the normalized association as I go from clustering to clustering. And what will, the intuitive knowledge or intuitive idea that we really want to capture with this technique of selecting the number of clusters in the partitioning is that clustering with k partitions represents an important scale if the normalized association is significantly larger than the normalized association of the optimized, the optimum partition with one more cluster. So what that's really saying is it buys me very little to take one of these clusters at level k and split it into two clusters. By merging them together, I've made a significant improvement. And then merging any two of those clusters at level k into k minus 1 clusters, the gain in doing that is very small. So I want a very large gain in coming from k plus 1 clusters up to k, and a small gain in going from k clusters to k minus 1 clusters. And so a simple assessment of that is a so-called, we'll call it a curvature metric because it's loosely related to that sort of notion. It's just the difference between the normalized association at k minus 1, then k plus 1 minus k. And what does that look like to give you some sort of intuition? Well, if I look at a ring of cliques, so cliques, what we have here is a group of 5 nodes that are completely connected, and then there's one connection between each one of these cliques. So the natural clustering here is to identify each clique as its individual cluster. And we looked at if we look at the curvature, you see that the maximum curvature is occurring at 24, which is the number of cliques in this ring. But you also see some interesting other little peaks which occur at multiples of 24. So what you can think of is that as I start merging nodes together, well, I can pick any 2 nodes out of these 5 and it's exactly equivalent. But once I've merged 2 from each one of these cliques, and I've done that twice, so there's 2 here, 2 here, I've now got an unbalanced situation where within each clique there's a set of 2, there's a set of 2, and then there's a set of 1. And so now I have to add that one node to a set of two to form a cluster of three and a cluster of two. And so this is going to be a change point in the partitioning that I'm identifying. Similarly, when I go past this 24, well, I can collapse two of these cliques into one single cluster, and that's going to give me a stable and sensible partitioning too. It's not as good as the one of 24 individual cliques, but it still has some good capturing some structure and some scale of this graph. Looking at a relatively small data set, but one that's a bit more real in a sense, and has some nastiness associated with it. This is the college football data set, where you have a set of leagues and the games between individual teams within those leagues. Here, again, we see this curvature graph. What we observe is that it's much sort of noisier. There are many more peaks in this case. But again, the maximum curvature is occurring at m equals 10, which is the number of divisions in this data set. So the curvature is providing some useful information even in these more realistic data sets. Another example, the hot topology, so getting a little bit closer back to some of the communication network people in the audience. Here we find that we have this very large peak at 123 as the number of clusters. And I've compared two of the other algorithms, fast unfolding, which is really a modularity-based algorithm. It's sort of a fast implementation in some ways of the Newman algorithms. I'll call them the Newman algorithms, based on optimizing the modularity. That finds that there are 27 clusters in this data set. InfoMap, this information theoretic approach, which really tries to fit a code and tries to encode the graph using a Hamming type code. That finds that there are 129 clusters. And then looking at the performance of this algorithm that we've proposed, we find as the maximization that there's 123 clusters. But it's interesting to observe the normalized association. How well is this algorithm performing? That's the metric that we'd like to optimize. We do see that the normalized association for 27, if we forced ourselves to pick, and there is a slight little peak here at 27. If we forced ourselves to pick that, then we get a significantly higher normalized association for that clustering. Interestingly too, we get a significantly lower modularity than the other algorithms. It's really showing that our algorithm is focusing on this metric of normalized association and has really little focus on modularity. Execution time. So this was one of the main motivations. What we were striving for was an algorithm that was very fast and would perform as well as the spectral clustering techniques which would require an eigen decomposition approach. And so as we increase here the graph isn't really big, but I'm just trying to show you what the sort of scaling behavior is. The algorithm that we've proposed, the Rosval InfoMap algorithm, Clauser-Newman-Moore algorithm, all of these scale approximately the same. They're all based on this hierarchical approach that I've outlined. They do different greedy searches locally. They optimize different metrics, but similar sorts of ideas. And the scaling is very reasonable as you increase the number of nodes in the graph. But if you look at the eigen decomposition approaches or some of the alternative approaches that are trying to maximize this normalized cut, then you really see this nasty growth in terms of the execution time. For 15,000 nodes, it's still not too bad, but the scaling becomes nastier and nastier. Hundreds of thousands of nodes, execution time in terms of both memory, so executing it in terms of both memory and time starts to become a little prohibitive. In terms of performance, just looking at the so-called LFR benchmarks, these are planted partition models where you're controlling the degree distribution of the graph, what we observe is that effectively, and the main conclusion here is that we're identifying graphs and clusterings, we're identifying clusterings with the same performance as the spectral algorithms, which is really what we set out to achieve. And the final performance issue that I'll observe is this effect of noise. So if we take the planted partition model, which is really optimally suited, it's the exact model that these normalized cut algorithms, it's sort of, if you looked at it as a modeling problem and say a Bayesian or a likelihood-based approach in order to optimize that, then the underlying model would really be a planted partition model. And what we've looked at here is, as I take a planted partition model and I start adding noise in terms of the weights of that planted partition model, how stable am I in terms of recapturing the underlying partition model? And we see that it's only minor, but the algorithm here is more stable than the algorithms based on the eigenvalue decomposition. So in summary, I've introduced a fast scalable clustering algorithm that strives to maximize the normalized association, which is an alternative to the spectral clustering approaches, and discussed in brief its application to content distribution in mobile social networks. Some future work is, and some important stuff, is theoretical bounds on performance, and the second point there, and Walter's at the back, performance validation. I always get nasty questions from Walter about performance validation. So I'll close there and take some questions if there are.
Comments or questions? Walter.
So you motivated this with an environment that seems to be very dynamic and unreliable. So does that algorithm handle that environment?
In terms of the clustering, you mean, or?
Yeah, I mean, so you have users going and coming at very fast rate. You have links that are not reliable at all.
Yeah, so I mean, I guess you can have a lot of arguments about underpinning all of this was an assumption that you have a stationary process of the contact times between users. And I guess depending on the scale at which you look at that, then whether that's true or not, it can be a major issue. This sort of system, what I propose in terms of mobile social networks, I think you really have to be looking at fairly delay-tolerant type systems where you're willing to let this content disperse through the network over a fairly long timescale. As you take the timescale a little bit longer, you're hoping that the fact that people have come and gone back, it's certainly there's parts of the distribution where it takes a long time to get to them, but the distribution that you can estimate with some degree of accuracy. But certainly the next setting is to try and track the clusterings. The next problem is maybe to track the clusterings, treat it as a dynamic graph, and then do optimization in a more dynamic fashion.
I have a question about noise. If you're doing sort of this agglomerative type of approach, it seems like it could be especially sensitive to sort of wild outliers. Like if you just got and then those first mergings, say, are just off because two people were measured as being close when in fact that was totally erroneous and it wasn't just a little bit of a perturbation but a wild error. And in some applications that wouldn't be an unreasonable type of model. Any thoughts about that? Because the spectral methods are a little bit more holistic, right?
Yeah, it's true. So we haven't done any analysis of how outliers would affect the performance of this algorithm, but I can certainly see that it would be. I would expect that it perhaps would fall down. Yeah. So we haven't. I mean, you can address that in terms of trying to go back down and come up a bit. maybe if you were faced with a situation where you expect that sort of thing to occur, you have to allow some recovery mechanisms when you do this sweep. This sort of greedy step can't just be a one-layer greedy step. It would have to be a little bit iterative in its nature. Yeah, so certainly what I've talked about here in terms of noise performance, it's in terms of slight perturbations of these weights, the weights between individual users. This is better than and more stable than the eigenvector methods. But as you suggest, I think if you were just to take one of them and tilt it, then I'd rather have an eigenvector method.
So Mark, did I get it right with your example of the hot topology that the modularity-based work and your work was they were looking in very different parts of the space, right?
Yeah.
So I'm wondering.
Although having said that, I guess the fast unfolding algorithm there finds a solution that has good normalized association and good modularity in a sense. So there are clusterings that will identify both for you. Our focus, the algorithm, is completely designed to choose the maximum normalized association, and that can lead to bad modularity.
So what I was leading to is, do you have some intuition for where the one is searching and where the others? For example, Mark can tell me if I'm wrong, but I thought that he and some colleagues had a spectral approximation, for example, to modularity-based optimization, and you have essentially a spectral base. I mean, is there a way to kind of write down the math and perhaps start looking at where it is they're looking in the space and why?
It's something that I haven't really looked at, but yeah, it's an interesting, and maybe Mark can provide a much better answer after Sue. I don't know. Yeah, I haven't looked at the connection between, I guess, there seems that there should be some sort of connection between all of these clustering. You're trying to do sort of the same thing.
You have two different surfaces in some sense of space. And
Yeah.
you're climbing around with different algorithms as well, but at least the mathematics may have a point of tangency. There may be a way to talk about the surfaces.
How about one more and then we'll make the transition? Okay?
I was thinking about the motivation of the work, and let's say that you are in a perfect, ideal environment where everything is static, and what you're optimizing is the information diffusion, right? Do you have any feeling whether there is a trade-off between diffusion and redundancy? Because in real systems, embedded nodes they tend to come across redundant information, and diffusion is not that important, right?
Yeah, so I guess there definitely could be a trade-off in that sense. So and there were two sort of problems that I was looking at that I posed. And in both cases I'm talking about distribution to everyone, which is this becomes even more of a problem if you're looking at one particular user or even just a small group of users. Then there's a lot of redundancy and a lot of unnecessary communication. In the case of distributing it to everyone, when you start looking at fountain code, when a person gets full and has enough to do the decoding, they don't need to do any more communication. And so that would reach a sort of natural limit in terms of the communication. You are paying the price for the coding. You're going to have to transmit some extra packets, and that's reasonably well understood in terms of how many packets you're going to have to pay the price for. In the other case, there can definitely be scenarios where you'll meet someone, he'll give you his latest update, and then 2 seconds later you'll meet someone else who has much fresher information, and it's going to be an issue.
Okay, let's make the transition now. Thanks very much, Mark.